All right, so we are still in section 4.1. We're talking about thermodynamics. And we're going to cover the last 2 pages of the notes, or at least a significant portion of them. This is a pretty dense unit, so this is something that you're going to want to watch the video, take notes, read your notes, go back and look at those textbook reading assignments that I gave you earlier. You really want to make sure that you don't miss things in this unit. Like everything else, it goes away for a while and then it comes back in another unit. So we want to make sure that we have it down now. So we are looking at example 2 now. And it's called Ideas About Heat. So the first thing it says, a student dissolves 10 grams of sodium hydroxide in 100 milliliters of distilled water. So we've got that up here. Notices that the temperature of the mixture increases from 25 degrees to 51.6 degrees Celsius. So what we're about to see is a very typical AP exam question. There's usually one every year where it'll tell you the situation and then it will say the student says, or the student states, or something like that. And you have to evaluate this student's idea. Is it correct or is it incorrect? Are they right or wrong? Do you agree or disagree? But you can't leave it there. You have to substantiate the entire thing. So the student states, the process of dissolving sodium hydroxide is endothermic. Because the temperature increases, so Q is greater than 0. So it says, do you agree or disagree? Why? Here's where the notes version is a little bit different because the AP question would stop after the why or explain. This goes on to say use the terms system, surroundings, heat, endothermic, and exothermic in your explanation. So I've got this pre-written for us to make the video shorter, so you might want to pause the video so you can write these things down. So a couple of things. First off, defining the system. The system is the process of dissolving the solid sodium hydroxide and making it aqueous. So I drew a little picture off to the side. This is the system. This is the actual process going on. And then the surroundings is the water. And so the surroundings is everything else. And yes, they are mixed together, so the system and the surroundings are very much blurred. But the system is the process of dissolving the sodium hydroxide, and the surroundings are the water. So the student is observing a temperature increase. And so if this were some sort of a container, and this is being dissolved in water, and we have a thermometer in here, we are measuring the temperature of the entire solution, or really what we're doing is measuring the temperature of the water. So the student is observing a temperature increase because heat is flowing from the system, which is the process of the solid turning into aqueous, and the heat is flowing from the sodium hydroxide process to the water. And so in terms of the process of the sodium hydroxide, which is a solid becoming aqueous, this is exothermic because it is releasing heat. If we were looking at the water, if the water was our system and the sodium hydroxide were, then it would be backwards. So if we were talking about just the water and there was something heating it up, yes, the water is endothermic. But the system is releasing energy to the surroundings. So if you look back up at the student's statement here, the process of dissolving the sodium hydroxide is endothermic. No, it's exothermic. So that part is wrong. Because the temperature increases, yes, the temperature of the water is increasing, and Q is greater than 0. So again, student, no. So you can't just say, yeah, I agree with the student. It's not like, if you're lab partner number 2, lab partner 1 did all the work, says this is what we think. Lab partner 2 says, yes, I agree. That's not really an acceptable thing. In part B, it says explain in terms of molecular motion what is happening when the temperature of the water is increasing. So what is happening here? Heat is being transferred from the process, the system, to the water, which is the surroundings. And so the temperature or the energy of the water is increasing because the heat energy is coming from the process into the water. So the energy of the water increases. The energy going into the water is causing the water to move more. It's causing more molecular motion. The water molecules are moving faster, which is kinetic energy. The kinetic energy is increasing. And so the temperature increases. Whenever the average kinetic energy increases, the temperature increases as well. They are directly proportional. Parts C and D, there is a lot of writing, and so we're going to do that in class. For part E, it says calculate the heat flow for this process, and the specific heat of water is 4.18 joules per gram degree Celsius. So figure out Q for this process. So we know the temperature of the mixture went from 25.0 Celsius to 51.6. This is one of those AP type things where our question is at the bottom of the page, but the information we need is all the way at the top of the page. So we know that the temperature is increasing, but we're talking about the temperature of the water increasing. We're also seeing here the specific heat of the water, and we're measuring the temperature of the water. So when we find Q for this process, it's actually going to be the Q of the water. Because my C is the water, I'm measuring the temperature of the water. Remember, my thermometer is measuring the water. And so we are going to have MC delta T. This is our formula. This is actually on the AP formula sheet, MC delta T. So the first thing, and we're talking about water here, right? This is the C for the water. This is the change in temperature for the water. So this needs to be the mass of the water. If you look up at the top of the page, we aren't actually given the mass of water. We're told that we have 100 milliliters of pure water or distilled water. And the way it works with water, 1 milliliter is 1 gram. And so we have 100 grams of water. So that is my mass of the water, 100 grams. Our specific heat is 4.18 joules per gram degree Celsius. And the delta T, go ahead and erase this. The delta T is the final temperature, 51.6 degrees Celsius. minus the initial temperature, 25.0 degrees Celsius. And once you put this into your calculator, you come up with a number that is positive 11,100, and that is joules, capital J. So this is the Q with respect to the water. This is how much heat the water is absorbing. If we want to know how much heat this reaction is releasing, here's what it looks like. The Q of the reaction, well, if the water absorbed this much heat, it means the reaction released that much heat. So Q for the reaction equals negative Q of the water, which means that this reaction released 11,100 joules. And so the process, remember, this process of dissolving was releasing energy. The water is heating up, it is absorbing that energy. In part F, it says calculate delta H of the dissolution for this process. And the process being sodium hydroxide solid becoming sodium hydroxide aqueous. So like we just wrote above, the Q for this process is the negative Q of the water. And so we have negative 11,100 joules. This is the amount of energy released by the sodium hydroxide as it's being dissolved. And so in order to figure out delta H, we have to know a couple of things. There's a formula, and this formula is not on the AP sheet, in part because it's really not that complex. Delta H is the Q of the reaction divided by the number of moles of the reaction. So what you end up with is how much heat divided by how many moles. So we know how much heat, that was 11,100. We need to know how many moles of sodium hydroxide did we have. And again, if you look all the way to the top of the page, we know that we put in 10.0 grams of sodium hydroxide. And so to turn this into moles, pretty quick conversion, 1 mole of sodium hydroxide is 40.0 grams of sodium hydroxide. This is the molar mass. You can calculate using the periodic table. And now we can calculate the moles, and it is 0.250 moles. 10 divided by 40, that's 1/4, 0.25. And so now we put it into our delta H formula. The little sub-label is not that important, but delta H for the dissolution equals the Q for the reaction divided by the number of moles in the reaction. And so we have So this is the part of it. We want to be a little more specific, and we will solve this, yes. But this is talking about moles of reaction, and we want to talk about moles of sodium hydroxide. And in this case, it's a 1-to-1 ratio, but it's helpful to make sure that we specify all of this stuff. So there's moles of sodium hydroxide. 1 mole of sodium hydroxide is 1 mole of the reaction. Once you get the hang of it, you can leave that step off as far as the writing is concerned. Just make sure that it's 1-to-1 and not something else. And lastly, delta H's have units of kilojoules per mole, and so we need to change this. There's 1,000 joules and 1 kilojoule. So once we go ahead and solve this, we find negative 44.5, and that is kilojoules per mole. In the near future, we'll have some labs. Thermodynamics has lots of labs that we can do, and so you'll see these formulas a lot, and you'll be able to put your hands on it and get some experience. Make it a little bit easier once you've got the hands on. So now we're moving into example 3, and it's talking about enthalpy of reaction. And so enthalpy is H, or delta H, and so we're looking for a delta H of reaction, and we're going to do it several different ways. So for everything in example 3, we are considering this reaction 2SO2 gas plus O2 gas yields 2SO3 gas. The first one is an experimental approach, and this is one of the ways that you'll do it in class in the lab. So basically what happens is we have the mass of a reactant, 9.71 grams of SO2, and it's reacting with excess oxygen gas. So we know a mass of a reactant, and we know it's going to release, or it did release, 15 kilojoules of energy. So delta H of the reaction is using the same formula that we just saw, the heat of the reaction divided by the number of moles of the reaction. The heat of the reaction they gave to us, it released 15 kilojoules of energy. So 15.0 kilojoules. If it released, it's negative. And then the number of moles of the reaction, which we actually have grams, but we can fix this. So let's go ahead and put our grams in here. And then we can do our conversion in the same formula. So if we find the molar mass of SO2, it is 64.07 grams of SO2 per 1 mole of SO2. And I like to cancel units as we go rather than at the end. So now I have kilojoules per moles of SO2, but we need it to be per moles of reaction. And here's the difference. Look at this reaction. If one of these reactions happen, we have to use 2 moles of SO2. And so that's a frequently missed piece of this puzzle where our delta H was off because we forgot to use the mole ratio. So for one whole reaction, we used 2 moles of SO2, and that's what this ratio is right here. Basically, whatever it happens, it's going to be the coefficient for your substance, and it's going to be 1 mole of reaction. So let's go ahead and solve this. And we should come out to negative 198 kilojoules per mole. And this is our delta H of the reaction, the enthalpy of the reaction, based on some experimental data. We have a lab where you will use this method to find the delta H of the reaction. In part B, we're using a different method. It is the products minus reactants method. And there's an AP formula for this. Here in the blue box, you see delta H, and it's got a degree sign. That means standard. That just means it's at a specific temperature, 25 degrees Celsius. So the delta H equals the sum of the delta HF, which is formation, we'll talk about in a minute. So the sum of the delta H's of the products minus the sum of the delta H's of the reactants. So delta HF is the enthalpy of reaction if you take the elements and put them together into the substance. Now the way it is, this is widely available data. For instance, in your textbook, the delta HF, or the heats of formation, are in Appendix C. You can find them in pages 1059 to 1061. There's a lot of numbers there. It's got delta H's for most substances that you can think of. So it wants us to use the products minus reactants method to find the heat of formation of SO2. So let's imagine that this is an AP chemistry test. We don't have this book. We can't go to Appendix C. So here's how it's saying. It says, find this one. By the way, here's the delta H formation of SO3. And then it says go. One last piece of information, use the delta H of reaction from part A. So let's just start with a formula and try to make sense of what's going on. Delta H of reaction, delta HF of the products, minus all of the delta HFs of the reactants. These sigmas don't need to show up once you actually start using the formula. So let's take a look at what is the delta H of the products. And we only have one product. And here's some, let's do it on the next slide. The delta HF of the products. So we have to consider two things. One, the delta H of the substance, and two, the coefficient. So 2 here. So we have 2 moles of this SO3, and it's going to be times the delta HF of SO3. And that's it for the products. Then minus the reactants, we have 2 moles of the SO2 plus sigma means sum, so we're adding. plus we have 1 mole of the oxygen, which we'll need to figure out. All right, so let's put in some numbers and figure this out as we go. So our delta H for the reaction was negative 198 kilojoules per mole. And let's see, we're looking for delta H of SO2, and that's this one right here. All right, so we're going to have 2 moles, and the delta HF SO3 is negative 396 kilojoules per mole. So it's cancel as we go along. The moles will be canceled. So minus the next one. So we have 2 moles of, we don't actually know what this is, that's what we're looking for. Plus we have 1 mole, and the delta HF for O2. Now the delta HF, remember this degree sign means the standard state. And so an important piece of information, this is an element in its standard state. When an element is in its standard state, delta HF is 0. And so for our oxygen here, 0, which means we can cut this whole part out right there. So now it becomes this situation of we just need to solve for the delta H of SO2. So negative 198 kilojoules per mole equals all right, so once you solve for everything, you'll find delta HF for SO2 equals negative 297. That is kilojoules per mole. If you look at part C, we're talking about something called Hess's law. We also have a lab for Hess's law. Like I said, thermodynamics has a lot of labs that can be done. You've seen something like this before. So in the equilibrium unit, we could use a couple of reactions and put them together to find out the equilibrium constant for a different reaction that was related. And this is a similar idea. So we're going to maybe double these, maybe flip them. to get to the point where we have the one reaction that you see at the top, the reaction that we've been working with. So by the end of all this, we want to have the delta H for this reaction. So this is what we're looking for. And we have three reactions that all happen to make this one reaction. So reaction one, we have, here's the reaction, here's delta H. Same for reaction two, we have a delta H. Reaction three, we have a delta H. So we need to learn how to put these together in order to find the delta H for this sum reaction, the 2SO2 plus O2 yields 2SO3. So here's what I look at. I try to use these one at a time. If you're staring at all three reactions right now, it's going to make it a little more difficult. So narrow your focus and let's just look at reaction one for a minute. So if I compare reaction one with the reaction directly above it, I see a couple of things. I see that O2 is a reactant, and yeah, up here it should be a reactant too. But then I look over here and my SO2s are in the products when they should be in the reactants. So let's take a look here. Are there SO2s anywhere else? It doesn't show up in reaction 2. SO2 doesn't show up in reaction 3. And so really this is on the wrong side. This needs to be a reactant. So I'm going to make some notes as we go along here. I'm going to have to flip reaction 1. Just to get SO2 on the right side, on the reactant side. Now that does pose a problem with the oxygens because now they're in the products, but this is not the only reaction that has oxygen. Reaction 3 also has oxygen. So once we flip that, I'm going to go ahead and rewrite reaction 1 for now. So I flip number 1, and that gives me this reaction. And this is important. When you flip the reaction, you end up flipping the sign of the delta H. And so this reaction is now negative of the delta H1, which means it is positive 1124 kilojoules per mole. Whatever you do to the reaction happens to the delta H. So now we have reactions 2 and 3 to work with, and it's kind of hard to tell which one to work with first. So if we look at reaction 2, H2O is an intermediate, H2SO4 is an intermediate, meaning they don't show up in this larger reaction. But SO3 does, and SO3 needs to be a product, which probably means I have to flip it just to get it on the other side. If you look at reaction 3, SO3 doesn't show up here, so we have to flip it here. So go ahead and flip it. This is the only place where the SO3 shows up. And in the final reaction, it should have a coefficient of 2. And so we have to do something else to this reaction. We have to flip, and we have to double everything so that we get the right coefficients. This is one of those things that takes practice. After a little bit of trial and error, it becomes significantly easier. So flip and double number 2, and so that is 2H2SO4 yielding 2H2O plus 2SO3. Now for the delta H. So the delta H has to change, so it's not just going to be the delta H of reaction 2. We flipped it, so it's negative. We changed the sign. And we doubled it, so we have to double the delta H. So when we flip and double this one, we find it is positive 264 kilojoules per mole. Now the third reaction, it has H2SO4, which we needed to cancel. And it has H2S, which we need to cancel. So what we're going to do with this one, the sides are okay, but we have to double this one. So we're going to double reaction 3. And we'll write it down here, double number 3. 2H2S plus 4O2 yields 2H2SO4. And for this one, the delta H for reaction 3, we need to double it. So we're multiplying by 2. But the sign stays the same because we did not flip this reaction. So the sign is going to remain as it is. So we've got negative 1,586 kilojoules per mole. Now here's what you do with it. You basically draw a long line here, and you're going to add everything together. You're going to add the reactions together. You're going to add the delta H's together. Before I write a bunch of things another time, I want to see what's going to cancel. So let's look at some of the intermediates here. We've got 2 waters and 2 waters, and they're on opposite sides of the arrows. Cancel. 2SO2, that's good, I want that to be there. 2H2S. So that's a product here. It also shows up in reaction 3, 2H2S, 2H2S, cancel. What else do we have? We have 2H2SO4, 2H2SO4, cancel. So we have SO2, SO3, and we have oxygen. Our only problem, the last piece of this puzzle, is the oxygen. I have 4 oxygens in the reactants, I have 3 oxygens in the products, and I should only have 1 in the overall reaction. And so this means that these 3 oxygens are going to cancel out with 3 of these oxygens, which leaves me with 1. Now I can put these together. My reaction is 2SO2 plus, we have 1 oxygen gas, that's good, yielding 2SO3. So the reaction matches. And so what we're going to do for this is add these 3 numbers. So when we find the delta H of the reaction, so we add these 3 together and find it as negative 198 kilojoules per mole. Once you get to try this out, it gets a little bit easier. Take a look at this. We can double check our work here. According to Hess's law, our delta H of reaction is negative 198. According to our experimental value in part A, our delta H of reaction was negative 198. And so it looks good. Now, when we do this in our lab, it's probably not going to look that good if the delta H of reaction from Hess's law was negative 198. The one in our experiment could be significantly different. It could be 170, it could be 150. You never know. There's a lot of chances for experimental error in thermochemistry. So the last one is enthalpy of reaction in terms of bond energy. And this is something that we'll do later in class. I don't think that we're ready to pile this on yet. But the basis of what's happening is we're looking at how much energy does it take to break this bond, and how much energy does it take to make this one, and this one, and this one. So in terms of bond energy, we want to break all the bonds of the reactants, and we want to put together all the bonds of the products. How much energy does it take? So that's the short version, and we will get to that later on. But we'll definitely do it because this has showed up on the AP exam several times in recent years, and so it's worth us going over.